Okay, so in part one of this project, figuring out how long, looking at exponential decay and figuring out how long it would take for Tylenol to leave your system, the first thing we did was we modeled how long it would take the Tylenol to leave the system. And I'll remind you that we made the assumption that Tylenol leaves the body, like half of the amount will be gone every 3 hours. And so we wrote a model. And the model that we made looks something like this. The amount that you'll have after a certain amount of time, y, will be equal to the beginning amount. And when we made the model, we said the beginning amount would be 325 milligrams. That's the amount in one tablet of regular strength Tylenol. We said we would multiply that times 0.5 raised to the power of t divided by 3. Now, we're going to make a couple of modifications because we don't love the idea that this exponent has a divided by 3. But in order for me to explain how we're going to fix that, I'm going to back up a little bit, and we're going to go through some prior knowledge that you should have, and to show you how I'm going to simplify this just a little bit. So if we have something like x to the power of 2 and we raise it to the power of 3, we end up getting x times x 3 times. So we'll do that again, and we'll do that again. And when we multiply all those x's together, you'll notice you'll get x to the 6th. And that might lead us to believe that x to the power of 2 raised to the power of 3 is the same as x raised to the power of 2 times the power of 3. And if you believe that's true, it turns out that is actually correct. Now, what we're going to do is we're going to use this to back this out over here. See, if we have something like x raised to the power of t divided by 3, that is actually the same as x raised to the power of t times 1/3. Okay, t times 1/3 is t divided by 3. Remember, you can do something like t over 1 times 1 over 3, and you get your t over 3. Okay, anyways, the point I'm trying to make is that if I can break it up like this, if I can break it up into two things, then I can make this guy equal to x raised to the power of 1/3, and then raise that to the power of t. And now I got t all by itself. So that's what we're going to do over here. So I'm going to go back to our model, and we're going to say the final amount will be equal to the initial amount, 325 milligrams, raised to the power, or times 0.5 raised to the power of 1/3, and then we'll raise that to the power of t. All I'm doing is breaking up this t divided by 3 so that it's two separate powers. And then the t becomes all by itself on the outside of the parentheses. Okay, next. Now we got to do 0.5 to the power of 1/3, which I will remind you that means cube root of 0.5, but regardless, we'll do it on the calculator. So let's see what that looks like. Ooh, hey, before I figure out what 0.5 to the power of 1/3 is, why don't you try it on your own? You can use a calculator, it's okay. Give it a shot. Pause the video, give it a try. In the meantime, I'm going to assume that you just did it and you paused the video, and now I'm going to try. I'm going to go ahead and raise 0.5 to the power of, and I'm going to use parentheses just to be safe, 1 divided by 3, close parentheses. So it's 0.5 raised to the power of 1 divided by 3. This 0.333 is just 1 divided by 3. I haven't hit equal yet. So here I go. Drum roll, please. Bam. So we end up getting 0.793 blah, 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 blah. I think I am going to round it to 0.794 just to be safe. Okay, so it's 0.7937. So if I want to round it to 3 decimal places, or the thousandths place, it'll be 0.794. So I'm going to go ahead and do that and replace this 0.5 to the 1/3 power with 0.794. Here goes nothing. Okay, so we rewrite the model. Y equals 325 raised times 0.794, I believe we said, and that is raised to the power of t. Now we've got a pretty good model. The only thing is that there's a little problem. If we read this new problem statement, in this new problem statement, what we're trying to do is we're trying to find out, when does the Tylenol that we took get down to the point where it's no longer effective, okay? And in our model, we assumed that we would take one Tylenol tablet, but typically people take two tablets, and that's what's recommended by the manufacturer. And that means that really you're taking 650 milligrams to start with. So we'd like to know what happens when we start with 650 milligrams and we get down to 200. In other words, 200 is the amount that we'll have after so much time has passed. And what we're really curious about is how much time will that be? So I'm going to go ahead and start writing. I'll use a different color so we can see that we're started on the next leg of our journey here. We want to know how long it'll take to get to 200. That's our final amount, or the amount at time t. And we want to start at 650 milligrams. That's 2 tablets of regular strength Tylenol. And we will multiply times 0.794, which, by the way, I'd like to point out is about 80%. And what we're really saying is that we know that after 3 hours, we lose 50% of whatever's in our system of Tylenol. All we're saying is after we did the math, now what we know is after 1 hour, we're going to lose about 80% of whatever was in our system. 1 hour is less than 3 hours, and so we only lose 80% instead of losing 50%. Okay, so just to make some sense of the numbers we're looking at here. We'll raise this to the power t, just like we did up here. And now now this is a little bit more than a model. Now we're taking the model and we're plugging in numbers, and what we'd like to do is find out how much time has passed. And you'll notice that the numbers are strange enough where it's not going to be easy to come up with a simple guess on this. One thing that we will do is we will try to make this a little simpler by dividing out 650 on both sides. And when we do, this gets canceled. So yay, that makes things a lot simpler. And so then we're kind of stuck with 200 over 650. And that is equal to 0.794 raised to the power of t. The only problem is that in order to figure out t, we're going to have to use logarithms. And in order to use logarithms, we're going to switch stuff around. Now, before I show you how to use logs, this is not the first time that I've demonstrated this. I'd like you to pause the video and see if you can find t on your own. Okay, I'm going to assume that you paused the video. I am now going to go ahead and show you how to use logs to find t. Okay, so here we go. So first of all, let me clear out some space. All right, in order to use logarithms, I'm just going to put this guy down here in the more familiar form that we're used to. So I'm going to go ahead and do 0.794 raised to the power of t, and I'll put that on the left-hand side of the equal sign. And then on the right-hand side, I'll have 200 divided by 650. We'll make that into a decimal in just a minute to make it so that we can use the calculator to do the math. Now, in order to convert, actually, let me make that into a decimal real quick because I want to have to do a little bit less writing when I write out the log here. So here's what it looks like as a decimal. By the way, I did get a decimal, but before we look at that, I'd like to point something out to you. I always like it if we can do a little bit of the math in our head if possible. It'd be real easy to cancel those zeros in our head, and if we did, we would just get 20 over 65. And by the way, it's about 1/3. We know it's about 1/3 because 20 over 60 is 1/3. It's a little bit maybe, yeah. So anyways, then the other thing is, once we get to 20 over 65, we can then go ahead and divide the top by 5 and divide the bottom by 5, and we get 4/13. Again, we're not entirely sure what decimal that is, so we'll go ahead and we'll look over here. So when I do 200 divided by 650, I get 0.3076 blah blah blah. We're going to round it to 3 decimal places because we did that with the 0.794. So we'll do 0.30. What do you think that's going to be rounded to? I see 0.30769. What do you think? I think it should be rounded to 0.308. 0.308. So we'll put in 0.308 over here. And when I do, I really should make a little correction, because if we're going to round, then really the equal sign no longer applies. It's really approximately, but I'm going to go ahead and just, I'm going to ignore that just for a moment. And we'll go ahead and convert into logs. And I'm going to remind you, when we want to do a conversion to a logarithm, we'll use the Weingarten rule. And when we do, it goes a little something like this. And that lets us rewrite this exponential equation as a logarithmic equation. And the way we do it is like this. We're going to go ahead and say log base, because the base is 0.794. We'll write the base as 0.794. It's always a little bit smaller than the letters in log and a little bit lower. And then we'll write of 0.308. So this should always be, the 0.308 should be, the bottom should be in line with the bottom of the word log. And then that is all equal to t. Again, all I'm doing is the Weingarten rule. I go from 0.794 to 0.308 to t. 0.794, 0.308 equals t. Okay, also I'd like to point out, well, that technically, if this works properly, whatever number we get for t, if we raise 0.794 to that power, we should get 0.308. Okay, so now we've got a little bit of work to do to figure out what this log, what the value is. So we're going to use a little trick that we used in our last video. And by the way, this is only going to be approximate. This will definitely only be approximate. The trick that we used in the last video was we used the change of base formula to convert the log from this form to common log form, in other words, base 10. So what we said was, and those squiggly lines are not too great looking. What we do is we'll rewrite this as log base 10 of 0.308, because our calculator will do log base 10. And we'll put that over log 0.794. Now I've lifted the 0.794 up. This is a log base 10 and a log base 10. And we can now use our calculator to calculate what those two are, and then we can divide by one another and get a result. You are welcome to try this on your own with your own calculator before me. Okay, here we go. Okay, so we're going to do, now in my calculator, strangely, I have to enter the 0.308 first, and then I hit log. In your calculator, it might be different. So I'm going to go ahead and hit log, and then we're going to divide that by 0.794, and I'm hopeful that this works, and then we're going to take the log of that. Okay, and so we've got log 0.308 divided by log 0.794. Sometimes it's worthwhile to put parentheses around the top of the fraction and the bottom of the fraction, just to make sure that the calculator follows PEMDAS. Certainly you don't want to lead it astray. Okay, the result we got does look wrong, so something is amiss here. I'm gonna need to double check the numbers real quick here. Okay, so I figured out what happened. It turned out that whatever I did in the calculator previously, it was still using that value or that result. And one of my clues that something was amiss was that I was getting a negative value, and typically time is not negative. So I kind of was suspicious something went wrong there. So let's go ahead and try this again. So I cleared it out so that we're starting with 0 on the calculator, and then we'll do 0.308. And we'll take the log of that, and we'll hit divide, and then we'll do 0.794, and we'll take the log of that, and then we will go ahead and divide. And when we do, we get a number that's a little more reasonable. This number is 5.1015.3. What the heck? I guess I'll round that to 3 decimal places, although I could get away with 2 easily, I'm sure. So we'll do that. That looks to me like 5.105. So 5.105. Now, what does that 5.105 mean again? It's t, and what's t? It's the number of hours. Okay, now when we started out and we made the model in the last video, we were looking at reducing by half every 3 hours, but we did a little manipulation here, and when we did, now t represents every 1 hour, and it's because we're losing. We're left with 80% every 1 hour after every 1 hour, not 50%. So anyways, the units here are going to be hours. So this will be 5.105 hours. And the result should not be that startling to us. In fact, what it does is it gives us a warm, fuzzy feeling that we did the math correctly and that Tylenol did the math correctly. Because I'd like to point out here that if you look at the information, Tylenol, the manufacturer of this headache drug we take, says that you should take 2 tablets every 4 to 6 hours. Well, good reason for that, because after about 5 hours, you're down to about 200 milligrams, and it's no longer going to be effective. So there you go. There's the math. Now, some of you may have questions and thoughts about this, and I hope that that's true, because there are all sorts of little interesting things that I didn't discuss. And if you have any questions or if you have any comments that you want to make, please let me know, and I'd be happy to discuss them. Just because I didn't say it here doesn't mean that there's not more to this. There is more to this. But this is not a bad little way to begin to get an understanding of exponential decay, and how it relates to biology and how it relates to drugs leaving our system, and also how logarithms can be used to help us isolate variables that we cannot isolate using any other techniques. All right, take good notes, take pictures, submit to this Google Classroom.